Hello everyone, my name is Yi-Shan. Today I'm going to present a digital flow for asynchronous VLSI systems, status update. This is an ongoing effort partly funded by DARPA IDEA project. And this is a collaboration of UT Austin team and Yale team. The team at UT Austin is led by Professor Pingali, and the team at Yale is led by Professor Manohar. First, a little bit about me. My name is Yi-Shan. I'm a PhD student from Department of Computer Science, University of Texas at Austin. I'm advised by Professor Pingali. I'm interested in parallelization and language design for domain-specific computation. Currently, I'm focusing on EDA algorithms, timing analysis, and simulation. And here's a list of my selected honors. I won Graph Challenge Champion at HPEC 2017, third place award at Tau Contest 2019, second place at Decathlon at ICCAT 2019, and participation award at Tau Contest 2020. Because there's no material commercial flow for automatic asynchronous circuit design, we need to build our own. And here is a picture that gives an overview to the whole tool chain. Blue boxes are modules from the ACT framework. Orange boxes are modules that are already parallelized using Galois, a C++ library for efficient parallelization for graph computing. Gray boxes are third-party modules. Currently, we borrow them from the Open Road framework. We take user design in ACT language and expand the design into ACT internal representation. Then we do technology mapping, during which we identify missing cells and characterize various parameters for those missing cells, like power, timing, and so on, into Liberty cell library format. ACT interacts with third-party modules through exporting ACT results into industry formats, like Verilog, SPICE, LeftDev, and so on. We interact with physical design tools using LeftDev format. After technology mapping, we derive the logic gate network representation for user designs, from which we can construct our timing graph. And Cyclone can take this timing graph to perform asynchronous timing analysis, and then report critical cycle ratio, arrival time, required time, correcting slack, performance slack, power consumption, and so on. Now let's go through physical design tools. We do floor planning by using ByPart, a min-cut multi-level graph partitioner and floor plan partitioner. We do placement by using DALI for gridded cells and using any off-the-shelf placer for standard cells. We do global routing using Sprout. And for detailed routing and layout finishing, we use any other third-party tools. To abstract out geometry information in timing analysis, we use SPAF to interact in between Cyclone and physical design tools. Note that many of the pieces are themselves papers, like Cyclone appeared in Async 2020, DALI appeared in ICCAT 2020, and Sprout appeared in ICCAT 2019. For more details, we refer the audience to the individual papers. In this talk, I'm going to go through the updates for 4 key components in our flow, namely Cyclone, an asynchronous timer and power analyzer, ByPart, a deterministic parallel hypergraph partitioner, DALI, a gridded cell placer, and AMC, an asynchronous memory compiler. Details for ANC can be found in our ASIC 2019 paper. First, Cyclone. Cyclone is a comprehensive async timing and power analyzer. We need to build Cyclone because the performance for asynchronous circuits needs to analyze cycles in the circuit explicitly for exact timing results. We cannot just break cycles and then leverage any off-the-shelf synchronous timer for timing analysis in asynchronous circuits. We enhance the functionality of Cyclone by supporting quasi-delay insensitive circuits with data and bundled data with logic timing constraints. We also integrate power analysis along with the timing analysis in Cyclone. We improve the performance of Cyclone in the following ways. First, we exploit module hierarchy to enable faster timing graph construction. Second, we parallelize various phases in Cyclone using Galois effectively. Specifically, we parallelize the following 4 phases in Cyclone. 1. Steady slew and delay computation. 2. Longest path forest construction in critical cycle ratio algorithm. 3. Timing propagation. And 4. Timing constraint checking. This table shows the performance on large circuits using Cyclone. B203 is a circuit in bundled data family. The other 3 circuits are from QDI family. The first 5 columns shows the property of circuits, their names, number of pins, cycle period in terms of nanoseconds, number of ticks on the critical cycles, and power consumption in milliwatts. The middle 2 columns shows the runtime to find out the maximum cycle ratio for a given circuit. In Cyclone, we use YTO algorithm to find out the maximum cycle ratio, and here shows the time in second and number of threads to achieve this runtime. And usually, maximum cycle ratio is found by linear programming, and Cplex is the state-of-the-art package for linear programming. So we compare the runtime with our YTO implementation against the Cplex solution. And here we find that we can always characterize the performance of any circuit faster than Cplex solution because we are adopting better cycle ratio algorithm. The rightmost 3 columns shows the full performance analysis by Cyclone. Sequential runtime in seconds, fast runtime in seconds, and number of threads used to achieve this runtime, and the speed up we observed through parallelization. Note that we can achieve 6 to 20 times self speed up through our parallelization strategy, and this is rare in timing analysis space. Now let's go through by part. By part is a deterministic parallel hypergraph partitioner. By default, we use mean cut partitioning. And we're given original hypergraph, and we try to reduce the problem size by merging nodes or hyperedges. So we form a series of smaller coarsened graphs. We call this process coarsening, and we can recursively apply this coarsening until the topmost graph is small enough. Then we partition this top level graph and then project the partition results to lower level of the graphs, and during which we can refine the partitioning results level by level. And this downward process is called refinement. We get the answer to our original partitioning problem by picking up the results for the lowest level of the graph in the refinement process. Now, by part, reduce the cut size by 15% compared to our previous version because we explore multiple scheduling policies when merging nodes. Also, we change our graph representation to use CSR format so that our runtime is 2 times faster now. And here's a detailed comparison of by part against the Zoltan, the fastest graph partitioner produced by Sandia Lab. On the left is the table showing graph statistics and the runtime from by part. We show number of nodes in a graph, number of hyperedges in a graph, number of edges in a graph in bipartite representation, and the runtime of by part using 1 thread in second. Also the runtime for by part using 14 threads in second. We see that by part consistently delivers 6 to 7 times self speed up during parallelization. On the right, it visualizes the comparison of by part and Zoltan. The x-axis shows the speed up normalized to Zoltan speed. The more to the right, the faster by part result is. And the y-axis shows the quality of our solution normalized to Zoltan's quality. The higher, the better. Now first, note that Zoltan cannot finish the largest graph we test, random 15 million, because it runs out of memory. Second, ByPart doesn't have any points dominated by Zoltan in both runtime and the solution quality. Actually, ByPart always runs faster than Zoltan, but for solution quality that varies input by input due to graph topology. Now let's go through DALI, a gridded cell placer. First, let me explain what is a gridded cell. Traditionally, we do placement with standard cells, which means all cells are of the same height or multiple of the standard cell height, like this picture shows. But for gridded cell, things are different. Each cell may have a different height from other cells, and the height may not be the multiple of the shortest cell in your rows. So we may introduce M-well design rule violations, P-well design rule violations, or power grid design rule violations, and so on. So we devised DALI, a gridded cell placement flow, to address this problem. The core problem being solved is weighted wire length optimization, subject to placement constraints like no cell overlap, design rule cleanness, and we need to handle gridded cells in this flow. Given a design, we run global placement and then run forward-backward legalization, after which we run well legalization and do the power grid design, and then generate the layout for routing. Now let's go into details for each phases in DALI. For global placement, we leverage existing techniques. We model wire length as a quadratic function to obtain a rough placement. During forward-backward legalization, we remove cell overlaps and avoid large cell displacement from the global placement suggestions. But note that we need to deal with gridded cells, which are harder than standard cells. After forward-backward legalization, we run well legalization, which we create mini rows by grouping gridded cells together into fixed width rows so that we can perform well legalization, which means we want to clean up design rule violations related to NP wells and also create NP wells and place well tapped cells for this group of gridded cells, mini rows. After well legalization, we are now ready to do power grid design, to lay out wires of VDD and ground and connect VDD and ground pins from the cells to power supply wires. And then we have the layout for routing. Now compared with standard cell methodology, gridded cell differs in many ways. In standard cell methodology, rows in the placement region are predefined or static, while in gridded cell methodology, rows in the placement region are dynamically formed by grouping gridded cells together. Therefore, NP wells and well-tapped cells are pre-placed in standard cell methodology, but those are mini-row based in gridded cell methodology. In terms of placement flow, global placement is shared in standard cell placement and DALI. For detail placement, standard cell placer can do detail placement for the whole design, but for DALI, detail placement is restricted within mini rows after well legalization. For well legalization, standard cell placer aligns cells to rows of cells, while DALI aligns cells to routing grids. For well legalization, standard cell placers implicitly do this by using abutment or filler cells, while in DALI, it explicitly constructs mini rows to perform well legalization. For power routing, standard cell placer implicitly do this by using abutment or filler cells, while in DALI, that is design dependent. Power routing is handled during placement explicitly. Dali has been used to tape out chips in 65 nanometer process. And here's the snapshot of the layout. Now let's go through the updates in AMC, Asynchronous Memory Compiler. We can construct memory compiler because it enables automatic generation for memory layouts to minimize the development cost of ASIC and processor designs, thanks for memory's high regularity in its layout. An asynchronous memory compiler is the first open source memory compiler that generates asynchronous pipeline SRAMs with high throughput and best latency. It provides GDS2 layout, SPICE netlist, left and lib files, and Verilog models of SRAM for variable size and configurations. AMC version 1 has been available on GitHub with a reference implementation for SCMOS. AMC supports common memory functions like read, write, and read-modify-write. It also provides synchronous interface so that you can include asynchronous memory in clocked design by wrapping asynchronous memory in this synchronous interface. AMC also provides SRAM built-in self-test, power gating, and write masking options. It eases the burden of designers by supporting different memory cell layouts and different bank orientations, so designers can evaluate different memories in their context. AMC is portable to new technology nodes. It has been successfully applied on 0.5 micrometer, 65 nanometer, 28 nanometer, and 12 nanometer FinFET technologies. The power gating in AMC supports sleep and wake-up modes. And here in the picture, we show ring-style power gating and daisy chain sleep signal distribution. The write masking option provides the flexibility to select which bits the write happens in an address line for a memory. When the select bit is high, that bit is overwritten. Otherwise, that bit retains its original content. And here in the picture, we show that enabling write masking option in AMC only incurs 4% overhead in memory area. To conclude, I've gone through updates in our asynchronous design toolchain, specifically for Cyclone, asynchronous timer and power analyzer, for ByPart, a deterministic parallel hypergraph partitioner, Dali, a gridded cell placer, and for AMC, an asynchronous memory compiler. In the future, we plan to make the flow timing driven, improve the flow in terms of quality of results and runtime, and support for more asynchronous logic families. Thanks for your attention, and please visit our GitHub repository to get more information and get access to the source code.